Your concrete house will crumble in 80 years. Chinese buildings from 1,500 years ago haven't even started aging. The difference? 15 construction methods so effective they were erased during a century of forced change. Between 1839 and 1949, Western powers didn't just redraw China's borders, they reshaped what counted as modern building in Chinese cities. Portland cement replaced rice mortar, steel bolts replaced nail-free joints, imported paint replaced 3,000-year-old wood treatments, not because Western methods were better, because they were faster. Scientists have now tested what was thrown away. The results are embarrassing. For us, here's what happened during the century of humiliation. Western engineers arrived in treaty ports with factory materials and tight deadlines. They looked at Chinese construction and saw primitives mixing food into walls. They saw carpenters refusing to use nails. They saw foundations made of sand and charcoal. So they killed it off in the cities, not always through laws, mostly through replacement and ridicule, through labelling thousand-year-old methods as backward. The twist? Lab results from the last 20 years show these methods beat their modern replacements. Better durability, better energy efficiency, better earthquake resistance. These aren't folk tales. These are techniques tested in modern labs from Tsinghua to Western universities and published in serious engineering and chemistry journals. Documented in guild records, still visible in structures standing after 600 to 2,000 years. We'll start where every building starts, with what you mix into the walls. Ancient masons cooked sweet rice into soup, then mixed it with slaked lime. Sounds like they were making lunch, not mortar. But here's what they knew. Rice contains amylopectin, a special sugar molecule. When you mix it with lime, these molecules fill tiny gaps. They stop big crystals from forming as the mortar hardens. The result? Mortar with a tighter structure than plain lime, more water resistant, more flexible during earthquakes. Sections of the Great Wall bonded with sticky rice mortar have survived intact for over 500 years. The sections repaired with Portland cement in the 1980s are already cracking. In 2010, a team publishing in an American Chemical Society journal tested ancient samples and new mixes. The rice-lime mix had higher strength and better water resistance than pure lime mortar. In many cases, it ages better than Portland cement because it doesn't get brittle. So why did it disappear? Late 1800s reform campaigns called organic additives wasteful food use. Portland cement was faster to mix, easier to control, and it came with the stamp of civilized European engineering. Speed mattered more than lasting power. But here's the thing about those ancient builders. Rice protected the walls, but the wood holding up the roof needed its own shield, and they found it dripping from a tree. For 3,000 years, Chinese builders soaked timber in Tung oil, pressed from Tung tree seeds. When exposed to air, Tung oil doesn't just dry, it transforms. The molecules link together and harden into a flexible shell that bonds inside the wood fibres. This isn't a surface coating, it's a complete change. Soft pine becomes waterproof, termite-proof, sun-resistant. It beats many synthetic coatings available today. Timber in elite buildings like the Forbidden City was treated with drying oils such as Tung oil from the early 1400s onward. 600 years later, the wood is still solid. No rot, no bug damage. The oil turned timber into something closer to plastic than wood. We think modern synthetic coatings are better, but Tung oil is a natural polymer that does what petroleum-based finishes do, without toxic fumes, without chemicals. And it lasts centuries, not decades. So why was it replaced? Colonial-era infrastructure brought in standardized lead-based paints and creosote preservatives as the official modern choice. Both poisonous, but both easy to mass-produce and regulate for big construction projects. A tree-based oil that needed local knowledge didn't fit the factory system. Oil sealed the wood. Rice sealed the stone. But in northern China, where winters crack concrete like glass, builders needed something to protect mortar from freezing. Their solution sounds gross. It also works perfectly. Builders in northern China mixed animal blood into their lime mortar, usually pig blood. The protein in blood creates tiny air bubbles throughout the mix. Why air bubbles matter? When water inside mortar freezes, it expands. In solid mortar, that expansion cracks the wall from inside, but those tiny bubbles give ice room to grow without breaking the structure around it. The wall survives winter after winter. This is the exact same idea modern engineers call Air-Entrainment. Today, we pay for synthetic chemicals to do what pig blood did for free. The chemistry is identical. Lab tests in recent years show that blood-modified lime mortar handles freeze-thaw cycles better than plain lime, with tiny air pockets improving durability in cold climates. Exactly the same principle as modern air-entrained concrete. So why was it banned? 20th century health movements classified all biological building materials as dirty. Modern codes ban blood in construction products. Fair from a cleanliness standpoint, but they didn't offer anything cheaper that worked as well. They just made the working solution illegal. The walls were sealed, insulated and freeze-proof. But none of that matters if the whole building falls when the ground shakes. And China sits on some of the most active earthquake zones on Earth, which is exactly why Chinese builders figured out something Western architecture didn't discover until the 1900s. Dougong are wooden bracket sets that lock together. No nails, no glue, no metal. Dozens of small timber pieces fit like a 3D puzzle between the column top and roof. During an earthquake, these brackets don't fight the force. They absorb it. The joints slide and turn against each other. They convert earthquake energy into heat through friction. The building sways, releases energy, and settles. It dances instead of breaking. The Forbidden City has survived numerous regional earthquakes since 1420. In laboratory shake table tests, scale models of Dougong structures have withstood extreme simulated seismic loads. The Dougong structure survived. The rigid modern comparison model collapsed. We think rigid connections are stronger. In earthquake zones, rigid is deadly. Dougong brackets are engineered flexibility. Modern earthquake engineering only adopted this idea in the late 1900s with base isolators and damper systems. So why were they abandoned? Dougong need decades of master-apprentice training. Each bracket set is hand-fitted. During the late Qing rush for fast modernisation, they were replaced by steel bolts and nails. Faster to install, but they make wood shatter under earthquake stress instead of bend. The brackets let the top of the building flex. But what about the bottom? Chinese builders had a solution for that too, and it would get you arrested on a modern job site. In many traditional Chinese timber halls, the massive wooden columns aren't anchored to the ground. They sit on polished stone bases, loose. The column rests on the stone through weight alone. During an earthquake, the ground jerks sideways. The stone base moves with it. The column, heavy and slow, stays behind, or slides slightly on the smooth surface. The building separates from the ground's movement. This is base isolation, the same idea used in the most advanced earthquake-proof skyscrapers today, done with a flat rock. The main hall of Foguang Temple, built in 857 AD, uses floating bases. It has survived every earthquake in Shanxi province for over 1,100 years. Modern base isolation systems using rubber pads and steel plates do the same thing, at thousands of times the cost. So why is this illegal now? Modern safety codes require all structural columns to be bolted to concrete foundations. A building that floats fails every inspection, even though it's proven safer in high earthquake zones. Columns floated on top, but what happened underneath the foundation was another layer of engineering entirely. Ming and Qing architects layered different materials under their foundations: sand, crushed stone and charcoal, sometimes several meters deep. Each layer has different density and bounce. When earthquake waves hit, they break apart and scatter at each boundary between layers, like noise-cancelling headphones breaking up sound waves. The shaking that reaches the building above is a fraction of what entered the ground below. Modern foundations are rigid and uniform. One solid concrete slab. This sends earthquake energy straight into the structure. The ancient layered approach is basically a passive earthquake filter. We now use similar ideas in advanced tuned mass damper systems. But the Chinese version needed no steel, no engineering degree, and no electricity. Archaeological work at major sites like the Temple of Heaven in Beijing has found layered foundations up to a couple of meters deep, sand-like material at the bottom, crushed stone in the middle, and lighter layers such as charcoal nearer the top, each layer packed and levelled. The temple has stood since 1420, zero structural damage from earthquakes. So why was this banned? Industrial building codes demand uniform, tested concrete foundations. A foundation made of sand and charcoal automatically fails modern inspections. Despite its 500-year track record, the foundation absorbed the shaking. The bases separated the columns, the brackets flexed the roof. But all these pieces were held together by one thing: joints. And Chinese joinery is where engineering becomes art. Sunmao is the Chinese system of wood joints. Hundreds of different joint types, each designed for a specific load. No nails, no screws, no metal, just wood cut to exact measurements. The genius is in what happens over time. Wood grows in humidity and shrinks in dry cold. Metal fasteners fight this movement. They stay rigid while wood pushes against them, eventually splitting the timber. Sunmao joints move with the wood. They breathe with the seasons. The joint gets tighter under load and looser when the load lifts. A self-adjusting connection. One joint type, called the dovetail mortise, can resist pull-apart forces in 3 directions at once, using only geometry. Modern engineers have tested traditional mortise and tenon joints against metal-bolted versions. The traditional joints often last longer under repeated stress, the kind earthquakes produce. Metal bolts create weak spots. The wood around the bolt eventually fails. Sunmao joints spread stress across the entire contact area. So why were they replaced? Factory-cut lumber and mass-produced metal brackets replaced Sunmao during industrial change. Not because they worked better, because they didn't need 10 years of training to use. The structure could flex, float, absorb, and self-adjust. But a building isn't just a frame. People have to live inside it. And in a country spanning from frozen Manchuria to tropical Guangdong, keeping humans comfortable without electricity was its own engineering challenge. The Kang is a heated brick platform, part bed, part stove, part heater, used across northern China for at least 2,500 years. A small fire burns in a box at one end. Hot gases travel through channels inside a massive brick platform before exiting through a chimney at the far end. The bricks soak up heat during the 20-minute burn. Then they give off that stored warmth for up to 10 hours. Fuel efficiency, extremely high. Much better than just burning the same fuel in a simple metal stove, because almost all the heat gets stored in the brick mass. A modern electric space heater converts electricity to heat at roughly 100% efficiency. But the electricity was generated at maybe 33% efficiency at the power plant. The Kang wins the full math. We think heated floors are a modern luxury. The Kang is heated surface technology, older than Roman heating systems, more efficient, and still used in rural northern China today. It heats the person, not the air, which makes more sense thermally. In a traditional northern Chinese home, the Kang takes up 1/3 of the living space. Families sleep on it in winter. The brick mass keeps surface temperature at 25 to 30 degrees Celsius through the night. One bundle of firewood, 10 hours of warmth. So why was it called backward? Western-style coal stoves were brought in as modern heating during reform periods. The Kang was labelled dirty and backward by urban reformers, even though the coal stoves they pushed were less efficient and filled rooms with smoke particles. The Kang solved winter, but what about summer? In southern China, where humidity turns buildings into steam rooms, builders engineered airflow without a single moving part. A Tianjing is a small, narrow, open courtyard at the centre of a house. Much taller than it is wide, it looks like wasted space. It's actually an engine. Hot air inside the house rises into the skywell. The narrow opening speeds up the airflow upward. This is mainly stack effect, with a Venturi-style speed-up as the air squeezes through the narrow opening. The rising air creates low pressure at the bottom. This pressure difference pulls cool, fresh air in through ground floor doors and windows. The house ventilates itself. No fans, no ducts, no electricity. Traditional Huizhou houses in Anhui province use skywells so well that inside temperatures can be 5 to 10 degrees Celsius cooler than outside on peak summer days. The skywell also collects rainwater, channels it into a central basin, and evaporation from that water further cools the incoming air. Cooling, ventilation, and water collection. One feature, 3 jobs. The size matters. A skywell that's too wide doesn't speed up airflow enough. Too narrow, and it blocks light. The best ratio is roughly 1:3, width to height. Builders didn't calculate this with math. They watched, they tested, they improved over generations. So why did this disappear? Overcrowding in treaty ports during colonial times led to apartment blocks that maximised floor space. The empty space a skywell needs was seen as waste. Modern buildings sealed themselves shut and became dependent on electric air conditioning. Cool air flowed in through the skywell, but the walls themselves were doing thermal work too, using a trick so simple it's almost insulting. Ancient palace and temple walls were often built with hollow spaces. 2 layers of material with a sealed air gap between them. Air conducts heat poorly. That trapped layer acts as a thermal buffer, slowing heat transfer in both directions. In summer, outside heat takes hours to get through. In winter, inside warmth stays in longer. The building keeps a stable temperature year-round with zero energy input. The walls of the Hall of Supreme Harmony in the Forbidden City are over 1 metre thick, but they're not solid. X-ray surveys found hollow chambers running up through the stonework. These air gaps reduce heat transfer by up to 40%, compared to solid walls of the same thickness. Modern insulation materials like fiberglass and foam do the same thing, but they break down, they soak up moisture, they need replacement. An air gap sealed in stone lasts as long as the wall itself. So why was this abandoned? Early 1900s fast build standards favoured solid, thin brick walls. Cheaper materials, less labour, faster completion. The thermal performance was worse, but the construction timeline was shorter. Speed, again, replaced performance. Materials that heal, joints that flex, foundations that filter, walls that breathe. But none of it matters if the roof fails. And in a country with monsoon seasons, the roof is where physics gets serious. The curved Chinese roof isn't decoration, it's fluid dynamics in clay tile. The curved shape speeds up rainwater as it travels down the slope. By the time it reaches the edge, it's moving fast enough to launch outward, away from the wooden foundation and column bases below. Straight roofs allow water to cling to the eaves through surface tension, dripping onto the wooden base. Curved roofs follow a Brachistochrone curve, the mathematically fastest path of descent. By accelerating the water, the roof converts gravitational potential into horizontal velocity, launching the stream clear of the foundation. The other keeps the base dry for centuries. We think the curve is cultural style. It's a calculated drainage solution. The overhang angle, the curve radius, and the tile shape are all designed to maximize throw distance while minimizing wind lift. Form followed function. The beauty was a bonus. Studies of traditional roof geometry suggest the curvature helps throw rainwater farther from wooden walls. The curve also creates pressure differences that help lift the water stream away from the building. So why was this banned? Victorian-style flat-sloped roofs were forced on new construction as symbols of modernity. The result? Faster rot in traditional timber neighbourhoods that had stayed dry for generations under curved roofs. the roof through water clear. But the beams holding that roof up had their own hidden trick, one that solved a problem before the building was even finished. Master builders installed horizontal roof beams with a deliberate upward bow, a slight curve toward the ceiling. This isn't a mistake, it's preloading. When the full weight of the roof is added, tiles, ridge beams, everything, the beam settles downward into a perfectly level, high-tension state. The wood fibres are compressed on top and stretched on bottom, locked in balance. The beam is stronger under load than it would be if installed flat. Mass-produced factory lumber is cut perfectly straight. Under roof weight, it immediately starts to sag, and that sag only gets worse over time. Ancient Chinese builders solved the sagging problem before construction even began by starting with a curve that gravity would flatten into perfection. Guild records from the Ming dynasty say beams should be selected with a natural upward curve of 1 to 2% of the length. For a 10-metre beam, that's 10 to 20 centimetres of initial rise. After the roof load is applied, the beam settles to within 2 centimetres of perfectly level, and it stays there. So why was this abandoned? Standardised lumber mills produce straight-cut beams. Pre-curved beams require hand selection of naturally curved timber and skilled assessment of load calculations. The industrial supply chain can't handle it. The beams held the roof through the water, but the walls themselves, the massive stone walls of forts and bridges, needed their own hidden reinforcement, and Chinese engineers hid it in plain sight. Hidden iron clamps shaped like bow ties were set into carved grooves on top of massive stone blocks, locking neighbouring stones together sideways. Molten iron was poured into the channel and left to cool, fusing the clamp to the stone. These ties provide sideways tensile strength. They prevent stones from sliding apart horizontally during floods, earthquakes, or ground settling. The wall can handle compression, stone is great at that, and tension, which stone alone cannot resist. Modern stonework relies on mortar and rebar for tensile strength. Rebar rusts, rust expands. Expansion cracks the stone from the inside out. The reinforcement destroys what it was meant to protect. Unlike modern rebar, which is buried in porous concrete, many of these iron ties were sealed in grooves with materials like lead, cutting off most oxygen and moisture. That drastically slows rust, so the reinforcement doesn't tear the stone apart. The Jiaozhou Bridge in Hebei Province, built in 605 AD, is the world's oldest standing open arch stone bridge. It uses iron ingot ties to lock the archstones together. 1,400 years later, the bridge still carries traffic. So why were these replaced? Mortar-only construction and rebar systems replaced ingot ties because they're faster to install and don't require custom stone cutting for each clamp. Speed and standardization won. Longevity lost. Iron held the stones together. But for most Chinese construction, especially rural, stone was a luxury. The most common building material was dirt, and what they did with dirt would make a modern structural engineer question everything. Builders embedded grids of bamboo or wooden strips inside rammed earth walls, creating a composite material. The earth handles compression. The bamboo handles tension. Together, they form a structure that behaves almost exactly like modern reinforced concrete. Bamboo has a tensile strength-to-weight ratio that rivals steel. It grows to harvest size in 3 to 5 years. It doesn't require mining, smelting, or a factory. And when embedded in earth, it's sealed from oxygen and moisture, the two things that make bamboo decay. Sections of the Hakatulo, massive circular rammed earth buildings in Fujian province, have stood for over 700 years. Some are 4 stories tall with walls over 1 metre thick at the base, reinforced with internal bamboo grids. They've survived earthquakes, typhoons, and even artillery bombardment during wartime. The bamboo grid is placed every 30 to 50 centimetres vertically as the earth is rammed. The strips are woven or tied together at crossings, creating a continuous tensile network. The earth locks the bamboo in place. The bamboo prevents the earth from cracking. So why was this banned? Rammed earth was labelled rural and backward by Western-trained architects who favoured uniform brick and mortar. Bamboo reinforcement doesn't appear in any international building code. A material with higher tensile strength-to-weight ratio than steel. Dismissed because it grows in the ground instead of coming from a factory. Bamboo reinforced the earth walls. But inside those walls, builders hid one more secret. A structural principle that modern codes call a defect, but physics calls a feature. The interior of many Chinese fortress and city walls was not solid. Builders filled the core with irregular rubble, broken stone, gravel, construction debris, packed between two outer faces of cut stone or rammed earth. During an earthquake or impact, those irregular rubble pieces shift against each other. Each shift converts motion energy into friction heat. The wall absorbs the blow by allowing its core to micro-adjust. A solid wall resists until it shatters completely. A rubble core wall adapts, releases energy, and survives. Modern inspection codes demand uniform materials throughout a wall. A wall filled with random rubble automatically fails. But the physics is clear. Energy release through internal friction is one of the most effective passive damping methods known. We use the same principle in modern car crumple zones. Controlled deformation absorbs impact, so the rigid cabin doesn't have to. The city walls of Xi'an, originally built during the Ming Dynasty, are 12 meters wide at the base. The outer faces are rammed earth and brick. The core is rubble. These walls have stood for over 600 years. They've survived multiple major earthquakes, including the 1556 Shanxi quake, the deadliest earthquake in recorded history. So why was this banned? Standardization. Modern codes require predictable, testable, uniform materials. A rubble core is variable by nature. Every wall is slightly different. It can't be reduced to a single spec sheet. And if it can't be standardized, it can't be approved, even if it beats the approved alternative. 15 techniques, 15 solutions that worked for centuries, some for thousands of years, all replaced. Not because they failed, because they were slow, required skill, and didn't fit on a factory production line. Here's what's worth thinking about. Every one of these methods was replaced during a period when China didn't get to choose its own standards. Colonial powers, treaty ports, and Western-trained reformers decided that modern meant European. And the building techniques that had kept structures standing through earthquakes, monsoons, and dynasties were relabeled as primitive. Scientists are now testing these methods in labs and publishing papers that confirm what village masons knew 1,000 years ago. Sticky Rice Mortar beats cement. Dougong Brackets beat steel bolts in earthquake tests. Bamboo reinforced earth rivals concrete. The data is in. The primitive methods were engineering. The real question isn't why ancient Chinese builders were so clever. It's why we were so quick to throw away what worked. If this changed how you think about what advanced really means, subscribe. This channel breaks down the engineering behind ancient structures that modern science is only now catching up to. More unreasonable cleverness, more forensic breakdowns, more proof that the past wasn't primitive. We just stopped paying attention.